Welcome to the SEI Podcast Series, a production of the Carnegie Mellon University Software Engineering Institute. The SEI is a federally funded research and development center sponsored by the U.S. Department of Defense. A transcript of today's podcast is posted on the SEI website at sei.cmu.edu/podcasts.
Hello, my name is Suzanne Miller. I'm a principal researcher here at the SEI, and I'm joined today by my colleague, Dave Shepard. We both work in the CDC Directorate of the SSD, the Software Solutions Division of the SEI. So welcome, David. I'm excited to be here to talk with you about digital engineering and how it intersects with DevSecOps, or Development Security Operations, as we know it. So before we get into that topic, our viewers like to know sort of who are you? What is it that brought you to the SEI, and what is it that brought you to working in digital engineering? Because that's not necessarily the thing we immediately think of when we think of DevSecOps. So over to you.
So digital engineering is a part of my current work as we try to help the DoD develop their plan for how digital engineering will be implemented across the department.
And that's very important. I mean, we know that there's a Congressional National Defense Authorization Act from a couple of years ago is really kind of what introduced this. We want to move in this direction, throughout the DoD. And so before we kind of get into digital engineering and DevSecOps, what is digital engineering and why, there's an argument that says, well, what's the SEI doing in digital engineering? We're software engineering and cybersecurity. This seems like this is sort of a higher level thing. Why are we doing this kind of work?
Right. So the sort of textbook definition that we're using for digital engineering is it is an integrated digital approach that uses authoritative sources of systems data and models as a continuum across disciplines to support lifecycle activities from concept through disposal. And what that really means is you're developing models for everything, not just for your software, but for all of your components of your system of systems, hardware and software. And you are storing those models in a singular repository of knowledge, both the models and the data that you use when you work with those models. And those models will be the single source that is used by all contractors and everyone working on the project.
So what is it? I can certainly argue that SEI knows about modeling. We've got things like, architecture analysis design language that are model-based kinds of engineering supports. But what is it that makes this a problem that the SEI really needs to work on? And this is where I see kind of the DevSecOps connection, because I see connections there. And so let's talk about them.
Yeah, so DevSecOps being thought of traditionally as like a software process, right? And that's fair because you are trying to integrate development and operations, and you're trying to do so in a way that ties in security throughout the life cycle of that development. Very software intensive, but our systems today are neither all software nor all hardware. So there's always some overlap. We've been looking at ways of integrating hardware integration concepts into our DevOps and DevSecOps thinking for a while now. It's sort of an interesting take coming from the other perspective, starting with the hardware mindset and looking at how to roll everything in, including the software. They're kind of different approaches how you go about doing that, right? And we can talk about that a little bit later.
So that sort of argues that, the digital engineering, we want models, software-based, obviously, models. And so somebody's got to develop that. Somebody's got to develop the repository. Somebody's got to develop the DevSecOps pipeline that's going to generate data about how all this stuff is working in the software, especially. So there is this confluence there's a lot of data that comes out of both of these areas, and there's a need for disciplined engineering in building the models, building the modeling languages, the modeling platforms, et cetera, et cetera. So what's your role in sort of working through all of that?
So can we talk a little bit about the differences in modeling of a hardware system versus what we typically do in software today, I think that's a good place to start. So, when we think of software modeling, a lot of people think that you're going to use SysML or something like that. I would argue that a lot of work goes into modeling software today across the industry that actually doesn't involve a formal modeling or a graphical language like SysML. There's a lot of different ways to capture a model, a lot of different ways to capture requirements, and our processes that we use for developing software today, like Agile, have a lot of tools that help with capturing models and information that's useful for developing the plan for how you're going to build something. So I think I wanted to say that because it's important to recognize that there are different ways that modeling happens today in software that do not necessarily look like what people expect software modeling might look like, right? With the SysML and tools like that. So I'm sorry, what was your question though?
So what's your role in sort of integrating that digital engineering DevSecOps perspective so that we get something that is disciplined, secure, and sort of covers that whole gamut?
So from my perspective, I work in DevOps. So I'm focused on infrastructure and tooling to help bring that pipeline of continuous integration and delivery together. So from where I sit in the process, it actually looks like a question of how digital engineering and DevOps will share resources and share information. So, for example, the DevOps world, the software development world, has kind of settled on Git as a de facto version control system.
Right.
Digital engineering, Git would not work real well for many digital engineering artifacts. They tend to be rather large, and they have their own tools for managing the versions of their models. So they're version controlled, and they need to reside somewhere. Where we tend to see them coming together is like on the cloud infrastructure that you're deploying your solution to. They can both live in the same space is the basic gist of that. And then it becomes a question of how much crossover you need between the two environments and how you bridge those, right? OpenMbe is a repository system for digital engineering artifacts as opposed to Git.
So that is actually one of the things that I'm seeing, and at least one of the customers that I work with, is that the tooling that's being used to build the platforms and the data repositories for digital engineering are coming from a different source and different idea base than what has been used for DevOps. So this is one of the challenges that the SEI is really a good place to deal with, is helping people to see where are the disconnects and what are the ways that we might approach the kind of integration that's needed, and where do we not need it? Because that's the other thing that I've learned in working in different modeling spaces, is that not everything needs to integrate, to the same level. And so finding out where we need that data to integrate is a really important part of this problem. And the DevOps folks, have a perspective on the data we need to get stuff through a pipeline. That's not necessarily the same task as informing, getting the results, for example, of that pipeline into new parameters in a model, right?
Yeah. So digital engineering is trying to capture the entire life cycle of the product. you can think of it in a sense as an extension of what used to be called product lifecycle management, or PLM, that started in places like the auto industry. That extension, it might seem natural from a hardware perspective to manage all of the artifacts and how things have changed over time with the hardware. That may seem natural to the hardware world. It's not something that's quite so natural or has been captured quite so rigorously with software. One of the things that I like to say is the best and worst thing about software is that you can change it.
Sure.
Right. And that's one of the things that has for a long time differentiated software from hardware systems. But we're trying to change that with digital engineering. We're trying to make it easier to change hardware. That starts with modeling, right? You can iterate faster on things when it's a model in software than you can if you actually have to instantiate a hardware version of that thing that you're building.
So that brings us to the idea that you talk about in the blog post, and it's out there quite a bit in the world, of this idea of a digital twin as being one of the focal points. That's kind of the mecca in some ways of digital engineering, is accomplishing a model that is a digital twin of the actual system as it is built. So that has an impact on testing requirements, right? We've already kind of in the DevSecOps world come up with ways of fast testing of requirements and fast feedback of testing in the CI/CD kind of world, continuous integration, continuous delivery kind of world. How does the digital twin kind of idea resonate with DevSecOps, or how is it different in a way that we really need to pay attention to, and not, as I'm doing right now, saying, well, we use some of the same ideas that we get fast test results in DevSecOps, we'll use those ideas in digital twins. So can you speak about that for a little bit?
Yeah. So, okay, let's start with the digital twin. So Dr. Roper, if you follow him, he would say that you have to kind of go all in if you want the maximum benefit out of digital engineering. What I take that to mean is you should have a digital model for everything in your system. And if you do that, then you can simulate your entire system at any time and work on that integration and really sort of get the robust testing and iteration on that system that you're developing. If you don't have the full model, or there's parts of it that have to be actually instantiated in hardware in order to do testing on them, then that slows your design and your ability to change things down. Modeling in software tends to look fairly different, right? So I'm trying to think. When you think simulations in software, it's usually like a video game sort of effect, right? Or like a car being driven around a closed track because you want to gather data or simulate some effect of a system. That's not typically how we think about building software, right? The product of software is a system that does something for you, but the modeling of that thing is not a graphical output for you. So our simulations in software tend to be unit tests, right? You're testing some functionality of the system.
So you're looking at a timing issue. So you're putting a trigger in place and you're running it through and looking at how long does it take, for example, as a simulation that you might do.
Does it perform as expected? Does it do what it's supposed to do? That's testing and writing different sorts of tests is how we typically do simulations of software systems. Not the whole build your system in a modeling application and then run it through some series of events that you can visualize. The output's like log files and things like that, right?
Right.
So, it's stimulation and it is testing, and you are getting similar effects, but the outputs look very different.
And so when we start thinking about digital engineering and we bring that perspective, I'll call it the video game perspective of visualization. Really what you're talking about when you talk about video game, you're talking about an ability to actually visualize the physical space that the product, whatever it is running in. That's different than how we think about it in software.
It is.
And so we
It
may
is.
not want to use exactly the same methods or expect the same things when we try and integrate our software models into that digital twin, for example.
Yeah, and one of the unique things that I think you get out of the simulation when you're doing a digital twin is that it's not just the visualization. You're also getting the data logged to log files and things like that, like you'd get with a software simulation. In some ways, it's probably more complete in that regard because you can actually look at your simulation in more dimensions. The effectiveness of your simulation, though, really comes down to how much effort you put into building that model, though.
Yep.
So, there's a place of where do you stop, right? How much fidelity do you need to simulate the system that you're trying to build? And I don't know that that's a question anyone really has a good answer to. I mean, we've seen jets, built from inception all the way down to, the full product delivered as digital models. Those they can build it. They can then go and build the actual jet off of that system. But you can still, just like anything that you're simulating, it, your ability to test it and understand where the problems are and your ability to resolve them still comes down to the people who are working with those models.
Well, and there are, the classic example is satellites. I can't have really, really high fidelity in the simulation of the effects of space. I have some level of fidelity I can achieve, but there's some stuff that, we're going to have to use other analytic methods to predict how things are going to happen after we launch. And we have to launch to be able to get some of that data. And that's expensive. And that's why we're doing this, right? And I think that's the trade-off you're talking about in terms of digital engineering is how much money do we, want to spend while we're essentially on the ground, wherever, whatever we're doing, before we kind of actually put our system into its intended environment where we don't have control over a lot of things and where it's very expensive to say, oops. I'm remembering the movie, what do you mean, oops? Independence Day is the movie I was remembering. We don't want a lot of those oopses out in the world. So we're actually, as our technology becomes more adept at doing those simulations, we want more fidelity in those models so that we don't have as many oops moments, when we're out in the environment. So that being said, what do you think are the sort of big rocks in kind of getting to a place where we really trust digital engineering, both for the hardware and trust it as one of the elements that we use for data in our DevSecOps pipelines? What are some of the research challenges that we really, if I'm somebody out in the world, I need to be aware, these are kind of my caveats. We're not there yet in some of these areas. What are some of the things you're seeing?
So, there's a ton of research areas that are potential, right? So one of the big ones from a technical perspective is there still isn't really an agreed upon definition of, for example, what is a digital twin?
Yeah.
Right. What was required for something to be called a digital twin? What are the file formats need to look like? How extensible should how does tooling tie into these things? Because over time, if you're building a model that you want to last for the life cycle of a product, which could actually be a very long time, you'd prefer that is something that the model, the data itself, especially if it's very large, can actually survive over time
Sure.
as your tooling and your needs for how you work with that model evolve. There's a lot of open questions there as to how to do that. Some of these models can get very large.
Sure.
So we'd like to get that right.
So that argues for some of the research that people are doing in data science research, and how do we preserve that data in a way that is going to be useful over tooling changes and other kinds of environment changes? How do we get stability in this very uncertain, kind of technology space, quite frankly?
Yeah, technology never stops changing. I wanted to say one thing, though, about your previous question on. So you were talking about how the hardware, from the hardware perspective, you have to deal with modeling and fidelity, and when's the right time that you can deploy that thing into a real environment. You deal with the same thing in software. You can do all kinds of testing, but until you actually put your system out on the internet, public facing connection, you don't really know what it's going to look like, right?
True enough.
There's a lot of testing is one of those activities that you always have to make that judgment call. When is it done? I don't know that that's a problem that we've solved yet.
Right. My experience is it's a research topic in and of itself, but it's also and it depends on context and how critical, how expensive, all those kinds of things. I don't think we're going to have you never take it below this level, for everything, right? Because that's not how our world works. So yeah. I want to switch a little bit to transition and learning. So if I'm somebody who's new to digital engineering, where do I learn about it? Some of the things you just talked about, we don't really have good standards for, what is a digital twin and things like that. How do I learn about both the opportunities and some of the caution areas? What are the resources that you would recommend that people take a look at?
Oh, wow. That's a great question, and one that I'm probably not the best person to answer it. I simply started using my search engine and going through the various tooling and frameworks
so
that
don't
are
be
out
modest, there. David, because one of the resources that is now available is your blog post.
Oh, true enough. Yeah. So as an introductory to what is digital engineering, that's out there. There's a lot of software projects out there on GitHub, for example, that have different efforts going on to provide tooling for the digital engineering space. Some of our collaborators in places like CERC, they have done a lot of work in this space as well.
So start with a blog post and kind of go from there. But this is a space, as you're saying, there's a lot written about, but I think the caveat is that it's still evolving. So make sure that you kind of look at multiple sources and make sure you understand the viewpoint of your sources. The example I'm going to use is I was at a meeting where there was a vendor who was, giving a presentation about the digital twin that they had built for this one type of component. And, when you started digging down just to the layer of sort of where we've been talking, what are the file formats and how do I exchange this with other things? They just went deer in the headlights. And their concept of digital twin was you take our model and you use it in our system, and there was no interface with the rest of the world. And I think that's probably one of the things that you want to look at when you're looking at resources is, are they closed or are they open?
It's easier to build self-contained vertical solutions than it is general solutions that are going to work across an ecosystem of products.
Or even it's not even so much a general solution, but put the hooks in your vertical solution so it can be interfaced with, in other areas. That was the thing that was completely missing from this solution.
Yeah, there are actually tools and frameworks out there that are going in that direction of trying to provide a general set of interfaces that hook into a lot of different products that are out there. That's a really hard problem. That's a complexity problem when you start getting into it. Every new solution's got to come with a new set of integrations to hook it into your authoritative source of truth,
right?
And make the tools, like you were saying, integrate in meaningful ways to provide functionality.
And so I think that's something that you mentioned. I want to sort of reiterate is that this is something that we're not on we're not done with this, right? Both in terms of research and adoption. And so everybody that Dr. Roper says go all in, but when you go all in, be ready for some of the things that are not done yet. You're going to be an explorer in this space. It's not something where you just can pull digital engineering tools off the shelf and it's really already done for you.
Yeah, once you start coming up with the use cases for how you would want the various toolings to integrate together, I think back to your research question, I think there's a big opportunity for some human-centered design research there to figure out what some of those use cases might look like when you start putting them together in tool format.
Okay. So what's next for you? I mean, we've got all these research opportunities. What are the areas you're interested in? What am I going to be talking with you about in 6 or 9 months? Because you've gone off and figured one of these areas out for us.
Well, so hopefully by then, the effort that I'm working on, we will have delivered our report to Congress on the state of digital engineering across the department, which is it's really interesting to see what a lot of the different programs are doing. Everybody, well, not everybody, but a lot of programs across the department are doing digital engineering in various forms. And we have been trying to capture that and really examine, kind of the best pieces of what everybody's doing to sort of put that together into something that the department can use.
Well, we'll have to put that on our calendar because I definitely want to have that conversation with you. Maybe we'll even do a panel with some of the other folks that are part of that. That would be fine.
Yes.
All right. Good. So this is good news for people that are trying to figure out whether or not their program should be, how they should be, that this report is coming. And that's probably, that's within the next 6 months that'll be done?
Yes.
Okay. So that's a good time frame. So I want to thank you for talking to us about this today. I am working on large programs, cyber physical system programs, where it's a big rock. And so the research that is going on here, I think is really important to everybody from the systems engineering through the software and test communities to really understand what can we get from digital engineering, what are we getting from it, and what can we hope to get from it as we move forward in the future. So thank you for the work that you're doing here, Dave. And I really look forward to that State of Digital Engineering report coming out. And I enjoyed your blog post. I want to tell our viewers that if you want to enjoy Dave's blog post, you just really want to go to insights.sei.cmu.edu. Easiest way to find blog post is to look look for the last name. In this case, it's Shepard. So find Dave Shepard and you will find his blog post on digital engineering. This podcast will be available lots of different places, and wherever you get your podcast, you'll be able to find it. Our transcript, as always, will have links in it directly to the blog post. As other resources become available, they'll get added into that too, things like the State of Digital Engineering report. And so you'll be able to see those on the transcript as well. If you have any questions, please feel free to send an email to info@sei.cmu.edu, and we'll do our best to answer those questions for you. So I want to thank Dave again, and I want to thank all of our viewers for participating in our podcast.
Thanks for joining us. This episode is available where you download podcasts, including SoundCloud, Stitcher, TuneIn Radio, Google Podcasts, and Apple Podcasts. It is also available on the SEI website at sei.cmu.edu/podcasts and the SEI's YouTube channel. This copyrighted work is made available through the Software Engineering Institute, a federally funded research and development center sponsored by the U.S. Department of Defense. For more information about the SEI and this work, please visit www.sei.cmu.edu. As always, if you have any questions, please don't hesitate to email us at info@sei.cmu.edu. Thank you.